Okay, so we were on oblique shocks. Okay, so when we wrote down the equations for oblique shocks, we saw that basically they're all same as the normal shocks, except that the parallel component of the velocities, they do not change across the oblique shock. So just to get a reminder, as in the normal shocks, we wrote out all the changes in properties in terms of the impinging Mach number. So we had an expression like this, right? So this is the Mach number behind the shock. So this we wrote down as right. So this is just to kind of remind ourselves. Then similarly, we wrote this for okay. Then again, this was for density, and then this is for the pressure. Okay, and right. So these are expressions that we had for a normal shock. Okay, so these are all expressions for a normal shock. Now, like we found out in that for oblique shocks, now the component parallel to the oblique shock does not change. Component of the velocity parallel to the oblique shock does not. There is no change in that. So basically, the changes across an oblique shock, changes in the flow properties across an oblique shock, are essentially governed by the normal component of the velocity change across it. Okay, so if I redraw this, so if this is my shock, right, and say this is my right. So okay, so this is V1 and this is V2. Okay, so then okay, so this is W1, and similarly we have this on the other side. So this is Q2 and this is W2. Okay, so okay, so this is from geometry, and we said that this angle is going to be beta and this angle is theta. Okay, this is the thing. Now what I'm trying to say here is that there is no change in this component of the velocity, which is that across the normal shock, W1 is equal to W2. This is what we proved from last time. Okay, so therefore the changes basically are happening because of the changes in the normal component here, which is U1 and U2. Now if I were to write the corresponding Mach number here as m, say N1 and m N2, right? So the changes basically are due to this velocity component. So therefore the change is because of this Mach number. So if I were to write this the expressions for all the changes in the properties in this with respect to this Mach number, then we should be able to use all the normal shock properties or from the tables. Okay, so let's do that. So if I were to do that, so here, so instead of this, so let us just write out these these expressions. So instead of this, if I were to write n here, and I've introduced n here, that will do the trick. So all I write here is n, all I write here is n, and so on and so forth. Right? So therefore these are essentially, so what you can see here, that I have written this in terms of, so I have written these, these relations now are basically valid for an oblique shock. Okay, and I write all of these expressions in terms of the normal Mach number over here. Okay. Okay, now taking from there, now this is our geometry. Now we can also write like this. Okay, now M2. So basically, if you look at, say, this triangle over here, so if I were to say A, B, and C, so this is, say, M2, right? The Mach number corresponding to this is M2, right? So if I were to write that, so this angle here, beta minus theta, right? So if I use this triangle, right, so what I get is right, we get this, or basically you can write M2 equal to okay, so this is an expression for M2. Now why is that important? Because this is the impinging Mach number. So this is my M1, right? This is my M1, and this is my M1, and how do I find out M2? Well, we'll need to go a slightly roundabout way because this is an oblique shock. Okay, unlike in the, if this was the impinging Mach number across a normal shock, we would just go look at the tables and find out the corresponding M2, right? In here though, I can't do that. First of all, I need to find out Mn2, which I can do from here, right? And which I can do from here, and know, because I know M1 and I can find out the normal component. So once I find Mn2 from here, so knowing the geometry from here, then I can find out M2. Okay, so this is the corresponding Mach number. Okay, now looking at this, okay, just if you look at this, just think about this. So basically this is beta. If you just look at the geometry over here, okay, if you just look at the geometry, so if beta is equal to pi by 2, then what do you get? Right? If beta is equal to pi by 2, so then what do you get? Just think about it. And if you also put pi by 2 over here, then what do we get? Okay, just think about it here as well. Okay. Okay, so now so basically I think you can see from here, just from the geometry, that if this beta is equal to pi by 2, you actually get a normal shock, isn't it? Then the shock is no more inclined. It is normal to this free stream velocity streamline. Okay. All right, so having said that, now let us use a couple of things over here. So okay, so this is my beta. So in that case, if this is my beta, then what do we get? So okay, so this is my beta, right? This is my beta, Okay, so then this again becomes my beta, right? So if I do this, right, if I do this, so then what I can find, let us do some geometry here. Let's call this ABC, and okay, so these, let us just name our triangles. So A, B, and C, and let's call this say D and E. Okay, so if I were to do that, okay, so then what we get is, from say this triangle A, D, E, right? I'm looking at this triangle over here. So then what I get is right? This is just from the geometry. So this is just from the geometry. This is tan beta. Okay, need to write this right. Okay, this is, so tan beta is equal to U1 by W1. And again, similarly, okay, so now we look at this triangle. So now we look at this triangle A, B, C. So we're looking at this triangle over here. So then what we get is tan, right? Tan beta minus theta is equal to U2 by W2. So U2 by W2, isn't it? Now, like we know that W1 is equal to W2, which is equal to W, say. Okay? So if that is true, then if we can write, in that case we can write right. So what we can write is U2 by U1. We can write this as U2 by U1. Okay. Now, okay, so I hope you understood what we did over here. So tan of beta minus theta is this. I just divided, basically, so if I write, say, this is 1, right? So all I did here is this, right? So if I do this, so basically what I get is tan of beta minus theta by tan of beta is U2 by U1, because like we said, W1 is equal to W2, right? We found that out before. Now, if we come over here, you can see we have an expression for U2 by U1 over here in terms of the normal component of the impinging Mach number, right? So I can actually write that expression, I can relate that expression with this. So if I do that, so what I'm saying is that this is also now a function of the impinging Mach number, right? And if I do the math, okay, if I do the math, what I will get is this. Tan theta is equal to 2 cot beta, okay, okay. So what we did over here is that this is what we're trying to do over here is that we are trying to connect the geometry, right? Trying to connect the geometry with the Mach number. Now, what is the purpose behind it? Okay. Now let's try and understand this a little bit. Okay. Now, for example, now what we were saying earlier on in terms of, say we have a supersonic flow coming like that, right? Say we have a supersonic flow coming like this, right? and it encounters, and say it encounters say a more an obstruction of this nature. So what we are most probably going to see is right a shock like that, a shock like that. So this is essentially the normal part of it, and this is a detached bow shock, right, and this will be a normal shock, right. This will be a normal shock in this case, right. However, let's change the picture a little bit. So say we have the same and okay, so this gets compressed and so on and so forth. Now we have the same thing, say over like that. Okay, so again we have, say, supersonic flow over here. Okay, now compared to this structure over here, right, this is more of a bluff kind of a body, right. So if I have something like this, instead if I have, say, something like this, if I say I have something like this, right, then what is the kind of structure that we're going to see? Right? What is the kind of structure that we're going to see? Are we going to encounter this sort of a shock, or what is it that's going to happen? Right? So what will happen here is that we are going to encounter basically an attached oblique shock. Right. So what we are essentially trying to calculate over here is that this is, say, my M1 and this is my M2, right, and in here, right, now this is an angle which I'm calling as beta, and this is an angle I'm calling as theta. Okay. So essentially if my shape of the body changes, then this is the kind of structure that we're going to see. Okay. Now the next question to ask is that, okay, now what governs this beta, right, or what governs this theta? So clearly what we see from here is that whether it will be an oblique shock or a normal shock, there is some connection with the geometry over here, right. There is some connection with this geometry. Now if we have, say, this sort of a this is the kind of, say, wedge we get, say we have a wedge like this or a corner like this, sharp corner like this, right. So we are encountering this, right. Now instead of this, what if we have something like this? Okay, let's say instead of this, say, what if we have, say, something like this? In that case, how will the geometry of this oblique shock change? Or will it change, or will it not change? Okay. Now clearly there is some connection of the geometry of the shock with the geometry of the body, right. So therefore if I have, say, a shock like this, or say I have a shock say like this, right. So if I have, say, so what I've drawn here is basically, say, 3 cases, right. So in these 3 cases, how is the geometry of the shock going to change, or is it going to change, right. Now based on that, so based on that, what we see over here, that the theta, right, which is the angle with which the Mach number behind the shock is deflected, right, because of the oblique shock. Now beta is the angle, beta is the angle of the oblique shock, okay, and M1 is the impinging Mach number. Okay. So therefore what we see is that these are connected. So the geometry of the shock is connected with the impinging Mach number, right? So this is the connection, and so therefore, if we do change the theta over here, there will be a corresponding change in beta. Or having said that, for a given theta and a given m1, beta is going to be a particular value or more than one value, right? Could it be more than one value for a given case of theta and m1? Let's see from here. So for a given case of, say, a theta, right, and m1, if you look at these equations, we will actually have two values of beta. Okay, so all right, so now this is an expression, therefore, right, again, so it gives us a connection between the geometry of the shock with the impinging Mach number, right? And this is this is the more very common theta beta m relationship, which is associated with shocks, with oblique shocks, right? And this again is given is available in charts in any normal regular textbook, right? This will be available from there, and you should be able to get your values very easily from there. Okay. So now, so let us just sort of look at this a little bit. Okay. Now the question is, like we said, that how are we exactly relating this geometry? So let us just look at that in, say, a little more in detail. Okay. So if, say, beta is given and m1 is given, now there is a corresponding maximum theta that this can attain. Right? There is a corresponding maximum theta, which means that for a given Mach number and beta, there is a corresponding theta max. Okay? There is a corresponding theta max. Now, what does this mean? What does this exactly mean when I say this? Let us take a look at that. Okay, let us sort of detail this out. Now, for example, so the point is that every time we have a wedge, should we have a attached oblique shock, or what? Okay, what do we encounter? So say this is the wedge. Oh, okay. Okay. So essentially, this is my theta, right? When you compare, so this is the geometry of the body. So this is the theta. Okay, and we have impinging Mach number, impinging Mach over here, and let us look at this case as well. This is also the theta, and we have the same, and I have the similar. Okay, so like if you look at this expression over here, now for a given, say, for a given Mach number and say a given beta. Okay, now let's basically just look at the math part of it over here. So for a given Mach number and a m1 and beta, there is a corresponding theta max. Okay, now what does this mean physically? Now, as you can see here, and like we were asking over here, that if I change this theta, right? If I change this theta, what happens to the geometry of the shock over here? Now, what we can see from here is that in here, so for both these cases, okay, that for this given Mach number and for a given beta, there is a corresponding theta max. Okay. There is a corresponding theta max. Now let us consider these two cases over here. Okay. Now this theta here, this theta of the body, okay, is greater than the theta max, okay, and this theta here is less than the theta max. What happens in either of these cases? What does that mean? What kind of a shock, or how is the geometry of the shock going to be defined? Okay, so what we have in this case, actually, in this case, that we are going to have essentially we will have an attached oblique shock, right? In this case, what we have is an attached oblique shock. Right? And what happens in this case? So their theta is less than theta max. Okay? Now just think about this. So in this case, we have an attached oblique shock. Okay? So now this theta is increased. Okay? This theta is increased, and so therefore there will be changes in the geometry of the oblique shock as well as we increase that theta furthermore. And this theta then becomes larger than theta max. In this case, what happens? In this case, what will happen is this. Of course, this is exaggerated, so just to try to make the point. So in this case, what we will see is a detached bow shock. Okay. So in this case, when the theta is greater than the theta max, what we will see is a detached bow shock. Okay. So from this, what I can sort of see for myself, and I hope you can infer the same, is that I have a smaller theta. Okay, and depending on the Mach number, we will have an oblique shock which is attached to the body, right? You start increasing this theta, right? You start increasing this theta. This angle beta also will probably, this is my beta, right? So this body kind of tries to move away the shock from itself, right? The more and more you increase it, this shock, the angle, the beta, the angle with the oblique shock makes also increases, and finally when the theta is large enough, larger than the maximum value of the theta, that it actually pushes away the shock farther from itself. It detaches itself and lands up out here. Okay, so then this becomes a detached bow shock. Okay, so this is for, say, wedges. Okay, now we could get a similar picture, say, for if I have a corner. Okay, if I encounter, if the same flow, it encounters a corner. So this is, typical wedge structure. So if I have, say, this is my M1. So what we could have is a structure like this. Okay, so basically I have a right. So I have a sharp corner like this. If I have a sharp corner like this, and I will pretty much get the same, if I have something like this. Okay, so if I have theta, say, greater than theta max, so in this case what we will have is a detached shock in front, like that. Okay, this, and similarly over here, if I have another corner like this. Okay, let's get that right. Okay, so okay, so if I have this, right, theta, you have less than theta max, so then this is M1. So in this case, Okay, that will be my attached shock. So in this case also we'll have an attached shock structure, and in this case we'll have a detached bow shock. So this is for basically corners, right, wedges and corners. So that is essentially the physical meaning what we take away from here. Okay, so this is the connection between the Mach number and the geometry of the body and the geometry of the shock hence generated. Okay, now again, now coming back to this relationship again, you can see, okay, make no mistake. So this is cos 2 beta. Okay, this is cos 2 beta. Okay, so if you look here, so basically for a given theta and m1, there are two values of the beta. Right? What does that mean? That for a given Mach number like this, right, and for the given geometry, there are two possibilities of this beta, right. There can be beta 1 and beta 2, right, two possibilities in which this shock is going to be generated. Okay. So now let us introduce the beta, right, which is the shock wave angle, into this equation and see what we get. See if we can infer some things more from this relationship. So this is the change in density across the oblique shock, right. So if I were to change that, so what I would get from here is this. Okay. Right, I get that, and then again P2 by P1, what I get again is okay. I hope you can see how we are introducing M1 here instead of the normal component. Okay. I think hopefully you can see that from here, right. I think we did that somewhere over here. Yeah. So if you look at this triangle here, A, D, and E. So all I'm trying to do is connect M and 1, and this is M1. Okay. This is M1. Okay. So if you take this triangle, so then sine beta, so essentially if you take that triangle, so here, okay, just to clarify this, so if you take triangle A, D, and E, so you get, say, sine beta is Mn1 by M1, right. So M1, so Mn1 is essentially M1 sine beta. That's all I've done over here. Okay, that's all I've done. So this is what we get from the expression over here, right? Now, so what I said over here is that now, so this is the relationship of. So what we're trying to do over here again is connect the change in geometries, the change in the flow properties with the geometry of the shock, right. Because what we're seeing over here is that if for a given Mach number, right, if I change the geometry of the body, the geometry of the shock also changes, right. So beta also changes. So the question is that important? Does that affect the change of my properties? It's okay, it's all right if this beta is smaller or this beta is larger. As long as my properties are not affected, the properties are not affected by the geometry or by the size of beta, I'm fine, right. What we see, however, that may not be true, right. So what we're trying to do over here is see if that will actually make any change. So what we did is that the change in properties over here, which is rho 2 by rho 1, we wrote that in terms of the Mach number, which of course is a defining parameter, and the shock wave angle, which is beta. And we did the same thing with the pressure. So this is what we it looks like. Now if you look over here, so therefore now if you look at this relationship, okay, now if we increase beta, what happens to rho 2 by rho 1 if we increase beta? And again, if we increase beta over here, what happens to P2 by P1? I think the best way to understand this is to actually put values of beta in there and probably and then get an expression for this. So what we'll do is we'll do a couple of problems and see if we understand that. Okay, so we'll do that. Okay, we'll do that in a bit. But just to think about it, so if you increase beta over here, what happens to rho 2 by rho 1? If we increase beta over here, what happens to P2 over P1? And what does that tell us about the nature of the shock? In the sense that is the shock becoming stronger, right? Or is the shock becoming weaker if we increase the shock wave angle, right? And the shock wave angle we can increase or decrease by a change in M1 and the geometry of the body. Okay, so I think what we shall sort of do is do a problem and then go ahead and see how this we can relate this. Okay, all right. So to do that, let us sort of look at this. Okay. Okay, so we have a uniform supersonic stream and the given values are M1, P1 is 1 atmospheres, T1 is 288 Kelvin, and this encounters a corner, right? This encounters a corner, something like that. So basically it is encountering, and so okay, and you know an oblique shock happens. Okay, so right, and that deflects it. So basically what happens is that physically, so you have a flow like that. Okay, so you have a flow like this, right? And physically then you have a corner over here. Physically we have a corner over here, and this is a incoming this is an incoming flow, and it has these properties. When it encounters a corner like that, it is basically deflected. Okay, it is basically deflected by 20 degrees. Okay, it is basically deflected by 20 degrees. Okay, so what we are basically then this is deflected, right, by 20 degrees. So this is a supersonic flow which is impinging. So now what we are basically seeing is that there is actually a shock wave, isn't it? So I think I should draw this right. Okay, so let's say, so therefore this is, okay, so say it is deflected by 20 degrees. Okay, and so essentially I can say that there is an attached shock over here, right? You could also draw this in this way, that you basically have, you know, a shock. This is a field, and this, it's deflecting it in such a way that this is 20 degrees. Okay, so this is essentially the geometry. It encounters, so I have a flow like this, encounters the corner, it deflects it by 20 degrees. So first things first, you know, what we need to find out is calculate the shock wave angle, okay, which is beta. Calculate beta, and then let us calculate P2, T2, M2, the stagnations behind the shock, right? So behind the shock, we need to calculate all of this. Can we do that? Okay. So now what we shall do now is to find out, okay, so to find out the corresponding beta, right? Now we have seen this relationship, theta, beta, m. So we know the theta, right? The theta is 20 degrees, m1 is 3. So from this expression, we should be able to find out the beta, right? Now this is something we can get from the charts, which is again available. So if I use that, okay, if I use that, so what I will get is this in here. So beta is equal to, if you look at that, so beta is equal to 37.5 degrees. Okay, so this is it. Now again, so now what is mn1? Now how do we calculate these? All we need to do is, like we have seen before, all of these things we can use the normal shock tables, provided we know what mn1 is. Okay, so we'll have to we can find these ratios with respect to mn1 and not m1. So now that we know m1, we know beta, we know theta, then how do we calculate mn1, right? So now mn1, so therefore mn1 is, right, m1 sine beta, right, and that is equal to 1.826. So mn1. Okay. Now corresponding to this mn1 from the charts of the tables, what we will get is from the, now we will go back to the normal shock tables, right? If I do that, then P2 by P1 is 3.723. This is what I got. T2 by T1 is 1 point, say that, and N2, right? So this is the M2 for normal shock, which is Mn2 over here, is equal to 0.6108. Okay, and we also get P, okay, let me write it better. Okay, so right, this also I get at 0.8011. Now all you need to do is basically, once you've calculated mn1, which is this, so just corresponding to that, we will get all these values from the normal shock tables. You just go look it up, and then this is all that we get. Now having known these ratios, now I believe you can find out all these values, because P1, T1 are all known, so therefore we can calculate, P1 is known, so we can calculate P2 from here, then T1 is known, we can calculate T2 from here, and what else do we need to calculate? So M2, so we can calculate M2 because we know Mn2, right, and P02 and T01. Okay, so if I do that, so let me just sort of okay, so if I do that, well, let me just write what I get. So P2 is essentially 3.723, right, atmospheres. Then what we get for T2 is 446.7 Kelvin. Then M2, how do we get? Mn2 sine of, now it is just math, okay? So we know beta, which is the deflection angle, and theta is given. Theta is 20 degrees. So, and this we basically, if you look at the geometry, the way we design it, if you look at the triangle ABC, I think, then you will get this. Okay. So then what you get here is this. Okay. Now, so again, what the now stagnation conditions. Now, how do we find out P naught 2 and P T naught 2? Okay. Now, corresponding to this M1, okay, corresponding to this M1 for say M1 equal to 3, we get values for P by P naught. This is also from the charts. We get P by P naught to be equal to 0.027. Write that. So therefore, from here I can calculate say P naught 1 by P1, right. So P naught 1 by P1, which is 36.74. Okay. So corresponding to this M1, what we get is the stagnation conditions like that. This is also from the chart, from the tables. So then P naught 1 by P1 is this. So you can see that P1 is something that is known to us. What we need, however, is P naught 2 by P naught 1. Okay. So this is it. So similarly, we will also get results. So again, we will again get for, okay, let's write it over here. So similarly, again, for M1 equal to 3, we get T by T naught as, right. So therefore, okay, so T naught 1 by T1 is basically 2.8. Okay. So if I do that, then the way we'll, how do we calculate P naught 2, right? So we need to calculate, okay, so what we need to calculate P naught 2 and T naught 2. Okay. So the way we get P naught 2 is, if we will just be a little clever and use this. Right. So this is something that we were able to find out corresponding to, yes, so we were able to calculate this with respect to N1, right. So we were able to find this out, and then using corresponding to M1, we were able to find these, right. So these are the stagnation conditions. So then we get P naught 2 in this fashion. It's just working with this. So what we get over here is, if you just use those values, and then what we get over here is, again, this is again just playing around. So T naught 2, T naught 1, right. So this is just using, right, and what we get here is 806.4 Kelvin, right. So this is what we get, and so right. So then this is, this is what we get. So okay, let's sort of stop here. So we'll do a little more with this problem and try and again address a little more in terms of what kind of a shock we get. Is it a strong shock or a weak shock? How do we decide that? Okay, depending on your Mach number, depending on the geometry of the body. Okay, so let us do that slightly more with this problem, and we'll discuss this in a little more detail. Okay, we'll stop here. Thanks.